All right, hello, greetings. Let's take a look at exercise 7.2. And so just as a note, exercise 2 essentially continues off of exercise 7.1, which we just solved in a separate screencast. But I'll solve this one, right, as if I didn't solve 7.1 just for your reference. So this is building upon, should be exercise 7.1. It is common that you measure the pressure drop via manometer and use this to calculate the velocity or in general the flow rate of the fluid. And we're going to recast the last exercise in such a problem. So air under normal conditions flows through a 4 millimeter diameter pipe. Over a 0.2 meter section of pipe, we measure that the pressure drop is 50 kilopascals. Knowing this, we wish to determine the average velocity of the fluid, so V. So for air under normal conditions, the density and viscosity are this, right? Those are in SI units. And then the pressure drop can be computed as this, where L is the length of the pipe, D is the diameter, rho is the density, V is the velocity, and F is the friction factor. Where we're told we have turbulent flow, so the friction factor can be calculated using the Colebrook equation, where epsilon over D is my relative roughness. Reynolds number is given as such. And then we're given two different cases of the roughness to consider. And for both of those, I provide the velocity as a reference, right? The velocity I can calculate as a reference, so you can use that to kind of troubleshoot or debug your code. Okay, and so first I just want to kind of go through this similar to what we had last time. Okay, so first, looking at equation 7.14. Okay, so we know L over D. Okay, we know 1/2 is 1/2, and we know rho. Okay, what I don't know is V. I don't know V, and I don't know F. Okay, and I know delta P in this case. So I know delta P. What I don't know is I don't know F, and I don't know V. Okay, so V is what I'm trying to solve for. So I don't know F, but the key is if I look at my expression for F, which is 7.15, F, right, is only a function of V, right? And what I mean by that is when I look at F, I know the relative roughness, okay? And then the only other term here is my Reynolds number, but within the Reynolds number, I know rho, I know D, and I know mu. Okay, so 7.15, okay, essentially what I have is F is just a function of V. Okay, so in 7.15, right, I just have the F as a function of V. Okay, in 7.14 here then, I'm trying to solve for V. Okay, I know dP, I know L over D, I know rho. Okay, I don't know F, but F is just a function of V. Cool. So what do I mean by that? So F is a function of V, and then I have this term V squared. And so what I'm going to have to do is I'm going to set up an air function, so I solve 7.14 via fzero. And so fzero is going to have an input of V, right? V is what I'm trying to solve for. So MATLAB will guess the value of V. It's going to pass it to my air function. And then with that guessed value of V, I can then go ahead and I can calculate my friction factor via equation 7.15 with that guessed value of V. Okay, and then my solution of 7.15 is likewise going to involve an fzero call to solve for F. Okay, so again, this equation here, 7.14, I'm going to have to create an air function to solve for V. Okay, so when fzero passes a value of V to that air function, okay, it'll plug in V squared here. Okay, then F is also just a function of V. So with that guess value of V, I'm then going to have another fzero call in which I refer to another air function, which is my Colebrook air function, using that value of V. All right, so we'll try and put this in action, right? And the great thing is this is going to require an fzero call to solve it. When I think about an air function to be used with fzero, all MATLAB cares is that I have a function with a single input and a single output. It doesn't care what happens, within that air function. All it wants to do is pass a variable to it, the variable I'm trying to solve for. And when I find the value of v that satisfies my equation or the variable, then it should return a value of 0. Okay, but let's try and put this in action. So I have my solution there from last time, and I'm just going to leave it. Okay, and what I'm going to start with is I'm going to call this function res is equal to velocity calc. Okay, and just like before, it's going to have an input of my roughness, okay, which is in millimeters. Okay, cool. And so then I'm going to come back over here. Okay, paste my function signature. So this is going to be a function to compute the velocity. And I'm going to do it in meters per second, or the average velocity. I'm going to try and put everything in SI units so I know that the units work out. So function to compute the average velocity in meters per second for a given roughness in millimeters for our specific problem, exercise 7.2, right? And what I mean by that is for, our specific flow problem. As I had mentioned kind of with 7.1 in class, is you could likewise make density, the length of the pipe, diameter of the pipe, all of those could be input parameters as well. And you could say write a script in which you pass all the information to this, but I'm just going to hard code all of that for now, and you could always generalize it if you wanted to. All right, so I'm going to start by inputting my parameters. So we know my diameter. So I'm going to use kind of an underscore millimeters when it's not an SI. So my diameter is 4 millimeters. Okay, bam. Okay. Okay, I will convert to meters. So my diameter in meters, this could be my diameter in millimeters divided by 1,000. Okay, bam. The length of my pipe. This is my length in meters. Pressure drop is in kilopascals. So dP in kilopascals is equal to 50. Okay, if I want dP in pascals, well then that's going to be my pressure drop in kilopascals times 1,000. Okay, diameter, length, pressure drop, density, rhos 1.23. Okay, I'll get my viscosity, 1.79. 1.79 e to the negative 5, and that's Newton second per meter squared. And that should be it. Okay, what I'm going to do is I'm going to calculate my relative roughness. So I won't necessarily convert my roughness, only because the only value I need is my relative roughness, epsilon over d. And so let me compute my relative roughness. Okay, it's dimensionless, and that way I don't have to worry about units. So that's going to be my roughness in millimeters divided by my diameter in millimeters. Okay, cool. Let me make this bigger. Okay, so I have all of my parameters, and now let's take this step by step. Okay, so if I'm going to calculate delta P, I'm going to need an error function for delta P. Okay, and when I think about my error function for delta P, I'm going to write this as a separate function, okay, because it's going to be more than one line, because I'm going to need to obtain this value of f. Okay, so let's do this. Okay, so I'm going to create a function. So res, and this is going to be my, call it dp error. Okay, and dp air function, it's going to have an input of velocity at the very least. Okay, this is my air function for my dp equation. Okay, I know it's going to have v, and what I'm going to do is I'm going to start typing in my function, my calculation, and as I type that in, I'll see what parameters I need from up above, additionally as input variables here. Okay. My air function can only have one input, which is going to be v, so I'll list all those other parameters that this function is going to need, and then I'll come back up here and I'll write an anonymous function that'll be able to share or pass that information to this function. Okay. So all right, so I need this equation. Okay, and that's pretty straightforward, I guess, right? So, well, my issue though is I'm going to need f, right? So delta p, right? It's fine. I know L over d, rho. I don't know v, right? So I'm going to, and then I'm going to need to get f. So all right. So the first thing I need to do is, I guess, I need to get f. Okay. So first I need to get f. Okay. So in order to get f, okay, I'm going to need my relative roughness, ED. Then I'm going to need my Reynolds number, and so that's going to require rho V. I already have V is what I'm trying to solve for. Rho V D. I'll take D in meters, mu. Okay. So let me compute my Reynolds number. So if I'm going to compute my Reynolds number, okay, my Reynolds number is rho times V times D divided by mu. Okay, and what's important here is this V here. Okay, eventually up here, I'm going to have an fzero call, and fzero is going to guess values of V. Okay, but for each guess value of V, all right, I'm going to have some knowledge of V, right? So I'm going to have knowledge of that guess value of V, which I can use in my calculation. Okay. So Reynolds is rho V D over mu, and then what I can do with that is, I think last time we just wrote an anonymous function for the air function for f. And I could do that here, right? That'll work just the same. Okay, so let me create an air function for f. I could create a separate function, or I could just create an anonymous function. So I'm going to create an air function for f. Okay, and that's going to be my Colebrook air, we called it. So it's going to have a single input, f, and then I'm going to write it as 1 divided by square root of f plus 2 times log base 10. The first term is ed divided by 3.7 plus 2.51 divided by Reynolds times the square root of f. Okay, so now within this air function, let me just delete this, delete some of the extra space. Within this air function, okay, I'm going to pass f to it. So this is a function to solve for f via my Colebrook equation, right? You could take a look at our last video. Within it is also ED and Reynolds. So my anonymous function, when I create it, exists within my function workspace. Within my function workspace, ED and RE already exist. And so it'll use the value that's currently stored in ED and RE at the time at which this anonymous function is created. So then to solve for my friction factor, so I'm going to call it FR, my friction factor, is going to be equal to, I'll use an fzero call. My first argument will be Colebrook air. Okay. Now, if you look at our video from 7.1, you can give it a search range. And so for the two cases we had in problem 1, you had a search range of something like 0.0001 to 10, right? It could be some larger value. The big thing with f is f needs to be greater than 0. So it can't be negative, right? The square root of a negative number will give me imaginaries. And it can't be 0 because then I have my undefined cases of 1 divided by 0. Okay? So it has to be greater than 0. And so when we played around with plot, we saw that we could give it a search range of something like 0.0001 to some larger number, or we just gave it an initial guess of something like 0.1, and that worked as well. And so I'm going to try just using 0.1 for now. And then if we get an error for any of our cases, then I'll have to come back and revisit it. So what will happen is when I give it an initial guess of 0.1, MATLAB will then use that as a starting point to try and identify or come up with its own bounds by searching out from that initial point. And so if it starts searching and gets to 0 or negatives, then I'm going to start to get some errors. My problem's going to fall apart. And then I might have to come in and try and come up with bounds instead. But for now, I'm just going to use that. Okay, and then with the value of my friction factor, well, then I can actually use my dP equation. Okay, so my air function, okay, is, remember, I just need to take this expression and rewrite it so it evaluates to 0 when I find the value of v that satisfies my equation. And so I'm going to write this as res is equal to dP. Oh, so besides mu, I need dP. So res is going to be dP minus my friction factor times L divided by D. Okay, L divided by D. Well, I guess I also need L as an input here. Okay. L divided by D times 0.5 times rho times v squared. Okay, cool. Now, so again, the interesting thing with my, well, let me write it up here. And then, well, all right, so I have this air function. Okay, v is what I'm trying to solve for, so it's going to be an input. But then I also have a list of parameters. These are my parameters from up here. Okay, but these are parameters that I need to have knowledge of down here. So within my function, I start with the current guess of v, because f0 is going to keep guessing values of v. With that current guess value of v, I'm going to guess or calculate the Reynolds with that current guess value of v. And then with that current guess value of v, okay, Reynolds, so with my current then guess value of Reynolds number, I'm going to define my Colebrook air function. And with my Colebrook air function then, I'm then going to solve for f. And then once I have f, I can calculate delta p. And so I'm going to calculate then my air function. I'll plug in that value of v here. I have f, which is only a function of v. And I can use that to then see if my essentially calculated value of delta p is equal to my actual delta p for that given v. When it is, right, this will evaluate to 0, and I found my value of v that satisfies my equation. Okay, now coming back up here, so this is my air function. Okay, the problem is with f0, my air function can only have a single input and a single output. So I'm going to create an anonymous function to pass parameters to our air function. Okay. And so I might call this like dp air. And I have a tendency to say like reduced. Reduce is, reducing the number of variables is equal to at. Okay. I want this air function to ultimately just have an input of v. And then what I'm going to do is when I pass the value of v to this anonymous function, I'm going to call this function with my guess value of v and then my parameters, which exist already here in my function workspace. Okay, this one doesn't light up. Why is that? It's because this is dp Pascal. I'm going to delete the underscore Pascal just because I said when I use SI units I won't add the underscore. Okay, and then there's L. Okay. Cool. And so then my final result. So now this will be solving for the velocity in meters per second. Okay, why? Because that's SI. And again, dp here, I'm using Pascal, so everything is in SI units. Relative roughness is dimensionless, right? That's why we kept roughness in millimeters. So solving for my velocity then, it's going to be another fzero call. And here's my function, dp air reduced. Then I need to give it a search range. Well, my velocity is going to be greater than 0. So I could, the first time through this, I could create a plot. Okay. So I could start with, say, fplot, dp air reduced, and I'll give it a search range of, say, 1 to 500. Okay. So let me actually do this. And, so again, what's going to happen here is you can think MATLAB's going to create a vector that goes from 1 to 500. You can think of it as using linspace. Then for each of those values of v in that vector, it's going to calculate the value of my air function, store that as a vector, and plot the results. So it'll complain because this isn't vectorized, but that's not going to happen because it actually has an fzero call. All right, so if I plot that, okay, I'm going to plot that by calling velocity calc. I'll give it my roughness of 0.26 millimeters. Okay, and that looks terrible. Okay, so let's see. It says the fzero cannot continue because the user supplied function handle matrix dimensions must agree. Okay, so it looks like I have some issue down here. So let's see, f1 divided by square root of f plus 2 times log 10 ed divided by 3.7 plus 2.51 divided by Reynolds times square root of f. So that looks fine. So we called that Colebrook air. Matrix dimensions must agree. So I must have a typo somewhere in there. So let me look. So rho vd divided by mu. Okay, where all of those parameters are scalars. You know what? I bet the issue is just with fplot, because it's probably trying to use some vector operations to actually compute or evaluate this. So my guess is fplot probably won't actually work because I have an fzero call. And so what I'm going to try, right, my first time around, is I'm just going to try fzero with my air function, and I'm going to give it a search range of, say, 1 to 500, and let's see what happens. So again, my guess is that what's going on here is nothing as a vector. So my guess is when I use fplot, right, it's probably trying to pass some vector of v to this air function here, and then that's causing an issue here when I try and use fzero on line 34. Okay, so cool. So when I don't plot and I just give it some big range, so 1 to 500, so 1 meter per second to 500, it works. I get 141.115, and that's exactly the reference value that I gave you. Okay. Cool. If I were to try 0015, 0015, I get 281.0068 meters per second, which agrees. Okay, great. So let's try and take a look at this. So here's my solution. This works. so just taking a look at it for a second to try and make a little more sense. Okay, the biggest issue is that when I look at my error function here, okay, remember, so I'm trying to solve for v. Okay, so f0 essentially is going to iterate on values of v until my equation is satisfied. Okay, where things can get a little confusing is, okay, I'm iterating on v's, and so for given value of v, so f0 is going to keep guessing different values of v. Each iteration, when it guesses a value of v, right, v is known, right, it exists within that workspace. So with that given value of v, I can then calculate my Reynolds number, and I can use that to solve my Colebrook equation for my friction factor, just like we did in 7.1. Okay, and this is where again the beauty is that within my error function, right, so this is my error function, it doesn't matter, right? MATLAB doesn't care what actually happens in my error function. All that it cares is that it's a single input, which in this case is going to be v, once I use the anonymous function to pass my parameters. That has a single input, which is the variable I'm trying to solve for, and a single output, right? A single output that's going to evaluate to 0 when I solve for the value of my variable that I'm looking for. Okay? So it doesn't care that this value of fr here, right, actually results from another f0 call. It doesn't care, right? All it cares is that I have a single input, v, and then I'm returning back a single output, which is the value of my error function, right, for that given guess of v. Doesn't matter what happens in between, right? And so it's perfectly fine or legitimate that I actually have an f0 call within that function. Okay, and so yeah, and just like for problem 7.1, here I use an anonymous function for my Colebrook equation. You just as well could have had another helper function, but then you would end up needing an anonymous function to pass additional information like ED and Reynolds to it. Okay, hope that helps. And again, you could have written a script to just demonstrate running this. Only issue I ran into this is fplot didn't work. So fplot didn't work for me. I suppose what I could do is I could evaluate my error function at those two endpoints. And so, if I wanted to check the bounds, I could just calculate or evaluate my error function at a velocity of 1 and 500 and just confirm it has opposite signs. And if it does, right, I could then proceed with my search. All right, let me know if you have any questions. If not, there's 7.2.